Yeah, please.
Thank
you. So it's my pleasure to Wilhelm Winter. I'm going to mute some people who are making some weird noises. Yes, so it's my pleasure to introduce Wilhelm Winter from the University of Münster. Wilhelm was, of course, my PhD advisor, so it's very nice to hear him give a talk in our seminar. And he will talk about completely positive approximations revisited. So please take it away.
Thank you so much. Thanks a lot for the invitation to come to Prague. It's, I hear it's a very nice city, and my internet research confirmed that. Maybe one day I'll get to see it in person. I've been to Prague a long time ago, but not mathematically. So yeah, this is about completely positive approximations. Most of this is joint work with Christian Courtney, but not all of it, and I'll indicate which projects these things came out from. It's a bit survey style, so you won't find actual proofs, but I'll try to indicate some of the technical steps, at least along the way. So it's about completely positive approximations for C-star algebras, just in case you've forgotten or never heard what a C-star algebra is. That's a Banach star algebra with the additional property that norm of x star x is the same as norm of x squared, and equivalently, it's a norm closed star subalgebra of bounded operators on some Hilbert space. And then the maps between C-star algebras, the typical maps are star homomorphisms. These are automatically continuous. And the more flexible kind of maps is the class of completely positive maps. And these map positive elements to positive element. Positive element is an element of the form x star x. So positive maps map positive to positive elements. And we also assume them to be linear. Thanks. And completely positive means even after you amplify to matrix algebras, then and apply the map entry-wise, then it still stays positive, and this is not automatic. Okay, so by a system of completely positive approximations for C-star algebra, it's a C-star algebra, I mean a system of diagrams here, or a net of diagrams here, where we have maps from A to F lambda and then back to A, such that the F lambda are all finite dimensional C-star algebras, and the phi lambda and the psi lambda are completely positive maps, and we want them to have a uniform norm bound. Often they will always be contractions, but not all the time. So we want a uniform norm bound on the maps phi lambda and psi lambda, and we want that their composition converges to the identity map on a point norm topology. Okay, so this is a system of approximations through finite dimensional C-star algebras, and the class of C-star algebras which admits such approximations is called nuclear C-star algebras, and they're equivalent characterizations of nuclearity, and this is closely related to the notion of amenability for groups, or groupoids, if you like. Okay, and just to remind you of a few remarkable facts about nuclear C-star algebras, there's a lot of very fancy results, especially in the context of von Neumann algebras. This, of course, Kahn's spectacular classification of injective 2-1 factors. Let me show you a few more sample results, which are maybe not so well known. One very classical result is this here: nuclear C-star algebras are precisely those with similarity degree 2. And I don't want to recall what similarity degree is, but let me say that this is a way to quantify the lack or the how far a C-star algebra is from satisfying the similarity property, and this I will define. So nuclear C-star algebras satisfy Caterson's similarity property, and this means whenever you have a bounded representation, which is not necessarily a star representation. So whenever you have a bounded representation on some Hilbert space, then this is similar to a star representation. And similar means there's an operator T, an invertible operator, such that T inverse representation T is then a star representation. Okay, and nuclear C-star algebras satisfy this property, and it's highly non-trivial. Another result concerns the Caterson-Castleer conjecture. Nuclear C-star algebras, separable nuclear C-star algebras, are stable under small perturbations. And let me say precisely what this means. If you have two C-star algebras, and I shouldn't have put nuclear here, so forget about that. If you have two C-star algebras which act on the same Hilbert space, and suppose one of them is separable and nuclear, and suppose that the unit balls are within a small number of each other. So this is a norm difference. Okay, so this means you take one unit ball here, and then you take the unit ball of the other C-star algebra, and this is close somehow. And if this happens, then the two C-star algebras are already isomorphic. All right, and never mind this number 1/420,000. This, of course, not optimal. Here's another more recent result. It's a combination of quite a few theorems, actually. Suppose you have, again, a C-star algebra, which is separable, simple, unital, and nuclear. And we want it not to be matrices, so it's supposed to be infinite dimensional. Okay, and then the following two statements are equivalent. First, A has finite nuclear dimension, and the second, A absorbs the Jiangsu algebra Z tensorally, A is Z stable. I will define nuclear dimension precisely in a moment. In this talk, I don't want to define or describe the Jiangsu algebra explicitly. You can think of this as either the smallest possible C-star version of the hyperfinite 2-1 factor. That's one way to think of it, and then of course I would have to say explicitly what I mean by smallest possible, so I certainly don't mean the complex numbers. You can also think of this as an infinite dimensional version of the complex numbers. And one other way to think of it would be to look at the interval, say something didn't work. At the interval, and then you take functions of the interval, and they take values in M2 tensor M3, and on this end they take values in M2 tensor the unit of M3, and here the unit of M2 tensor M3. So think of a bundle like this, bundle of continuous functions with values in matrix algebras. And then, in fact, we don't want just M2, we want M2 infinity, M3 infinity, these UHF algebras here, if you've seen them before. This is just M2, tensor M2, tensor M2, M3, tensor M3, tensor M3. And then think of an algebra like this, but a simplified version of this. So you can take an algebra of that, you can write down an inductive limit of such things, and you can arrange this limit to be simple, to have no non-trivial closed ideals. And then if this limit also has a unique tracial state, then it has to be the Jiangsu algebra. That's a very explicit description of this algebra. All right, and then it turns out that these two properties are equivalent. And then this plays a role for the classification program. State of the art of the program at the moment, more or less, is the following, at least in the universal case, the simple and universal case. Let's look at this class of C-star algebras here, which are C-star algebras of the form A tensor Z, where A is separable, simple, universal, nuclear, and satisfies the universal coefficient theorem, the UCT. And then theorem says that this class here is classified by the Elliott invariant. Now, I have to elaborate a little bit. This Elliott invariant here, I will explain what this is in a second. This is a functor, and then classified means whenever you have two elements in this class, and then you compute the value of the functor on these two elements, and it turns out that the results are isomorphic, then there's an isomorphism of C-star algebras which induces the isomorphism at level of the functor. Okay, and here K0 of A, this is C-star algebra K theory. This is essentially you take finitely generated projective modules over A, and then you turn these into a semi-group by modding out homotopy classes, and then you take the enveloping Grothendieck group of this, and then if you keep track of the image of the semi-group in K0 of A, then you get the positive part. You keep track of that. Keep track of the position of the unit, and or of the C-star algebra itself as a finitely generated projective module over itself. These are homotopy classes of unitaries in matrices over A. These are tracial states, a positive linear functionals with the trace property tau of x star x equals tau of x star. And then there's a pairing between traces and states, and these are positive characters on K0. There's a natural pairing, and then this is the invariant. And this C-star algebra K theory, I should say, this is in general much easier to compute and much easier to handle than algebraic K theory, for example. All right. And for all of these results, all the results I've shown you about nuclear C-star algebras, it's absolutely important to understand the completely positive approximations that I showed you in the beginning. So I said completely positive approximations, or the existence of completely positive approximations, is one way of defining nuclear C-star algebras or characterizing them. But for these results, it's absolutely key to understand these quite well. Okay, and that's really the structure of these approximations, these completely positive approximations. That's really the topic of the talk. So let me give a more refined version of the completely positive approximation property, which sometimes holds and sometimes not. This definition by Joachim Zacharias and myself, and an earlier version by Ebert Kirchberg and myself. So again, we look at the C-star algebra A, and we say this has nuclear dimension at most D. If the following holds, there's a system as before, A maps to finite dimensional C-star algebra F lambda, maps back to A, and there's a net of such things, such that these are completely positive approximations in the sense I mentioned earlier. So in particular, the composition phi lambda psi lambda converges in point norm topology to the identity map on A. But in addition, I want that the psi lambda are contractions, and also I want to be able for each lambda to decompose F lambda into D plus 1 summons. So these are finite dimensional C-star algebras, each one of them not necessarily matrix algebra. In general, each F lambda I will consist, will be a large sum of matrix algebras itself. And for each of these blocks here, if I restrict phi lambda to one of those, then I want phi lambda to be contractive. I want this restriction to be contractive, and I want it to have order 0. And this means this preserves orthogonality. So if I have x, if I have xy equals 0, and these are both in F lambda I, then this implies phi lambda of x, phi lambda of y equals 0. Okay, if x and y are in the same F lambda I. All right. So this is definition of nuclear dimension, and you should think of this orthogonality preserving property as disjointness preserving. If you've seen definition, if you remember the definition of Lebesgue covering dimension, then this is expressed in terms of disjointness of open sets, open set of members of an open cover, and this disjointness preserving property, this is modeled by this orthogonality. Okay. And it turns out you have to do a little bit, but it turns out that one can arrange, in addition, that the psi lambda are maybe not exactly approximately order 0, but approximately order 0. And this means if you have A and B in A and AB equals 0, then psi lambda of A times psi lambda of B at least converges to 0 in norm of the F lambda. All right, and if moreover you can choose the maps phi lambda to be contractive, then A has decomposition rank at most D. That's a different concept. Doesn't look very different, but there's a substantial difference between these two notions. Note that the phi lambda here are the sum of D plus 1 contractions, and therefore have norm D plus 1. Have norm at most D plus 1. Always, but if we can choose them to be contractive, then that's a stronger property, and then we say A has decomposition rank at most D. And in this case, we can even arrange that the psi lambda are not only approximately order 0, but they're in fact approximately multiplicative. So psi lambda of A, psi lambda of B converges to psi lambda of AB. All right. And for these two notions, it turns out that the maps psi lambda are less important than the maps phi lambda because one can maybe not read off the maps psi lambda from phi lambda, but you can recover from the phi lambda maps which are as good as the psi lambda. So here's a proposition. It's a one-sided version of this, and this has been used implicitly on a few occasions, but I don't think it's explicitly in the literature. So let me state this in the unital case. There's a non-unital version, but it's a little more complicated to state. Suppose A is a unital C-star algebra, and then the nuclear dimension of A is smaller d if and only if the following holds. For every finite subset, say curly F, which contains the unit of A, and we can assume F to be in the unit ball of the positive elements, and for every tolerance epsilon, there's a map phi from F to A, where F is a finite dimensional C-star algebra. And again, we want to be able to write F as a direct sum of d plus 1 C-star algebras and such that phi k, which is just the restriction of phi to fk, such that each of these is completely positive contractive and has order 0, so preserves orthogonality. And now the crucial condition is that for every A in this finite subset, curly F, there's an element in the unit ball of the finite dimensional C-star algebra F, in the positive unit ball. I call this B sub A, and since it's in the unit ball of F, it's a direct sum of BA case in the unit ball of the F case, such that this BA is mapped by phi almost to A. Okay, so A is approximated by these elements BA by the map phi, and we can recover the BA or at least their images in the following sense: when we take BA and then the kth part of BA, we map it to the C-star algebra A, we take phi k BAK, then this is almost the same as A times the image of the kth part of B of the unit. Okay. And note that in this characterization of nuclear dimension, and by the way, there's a very similar characterization for decomposition rank. In this characterization, the maps psi don't show up anymore. Okay, here I wrote down the characterization for decomposition rank. This is when you can choose B sub unit of A to be the unit of the finite dimensional C-star algebra. All right. It's worth pointing out that nuclear dimension and decomposition rank, they capture both algebraic and topological information. They're both more of a topological flavor on the face of it. And you can see this by comparing them to covering dimension, to topological covering dimension, Lebesgue covering dimension, and they just generalize covering dimension of a space to a non-commutative setting. But they also encode algebraic properties, for example, whether A is commutative. So it turns out that A is commutative if and only if the F lambda in the approximations are all commutative. And this is the reason for this is that these order zero summons require some rigidity of these approximations, which can then be observed at the level of the finite dimensional approximating algebras. And a statement like this would not be possible from the original completely positive approximation property. There, for the finite dimensional C-star algebra, you could even take individual matrix algebras as your finite dimensional approximating algebra, and then you cannot read off anything like commutativity from the approximations, at least not directly. Okay, and then as I already mentioned, if A is commutative, then it's of the form, if it's unital and commutative, it's of the form C of X for X compact Hausdorff space, and then nuclear dimension of C of X is just the dimension of X. Okay, and this also works in the non-unital case, of course. And then this is all very nice, and you have this correspondence between finite nuclear dimension and Z stability, which is quite surprising. This works in the simple setting for simple C-star algebras. But this is a property that a C-star algebra may or may not have. Even a nuclear C-star algebra need not to have finite nuclear dimension. It need not be Z stable, and topological space need not be finite dimensional. That's just how it is. It's nobody's fault. But one can ask, if you don't assume finite nuclear dimension, if you just assume nuclearity, can we maybe still find approximations in a similar style, which captures some of the nice properties of nuclear dimension approximations? And turns out that to some extent this is possible. So here's a theorem which is combination of work by Hirschberg, Kirchberg, White, and Brown, Carrion, White. Goes as follows. Suppose you have an arbitrary nuclear C-star algebra A, and then there's again a system of completely positive approximations as before, but in addition, we can write the phi lambda as convex combinations of contractive order zero maps. So recall, for finite nuclear dimension, I wanted to write the phi lambda as a sum of d plus 1 contractive order zero maps, and here we are, well, they are happy to admit as many summons as necessary. There's no global bound on the summons, but at least you get convex combinations. This is different. It's a different paradigm, really. And in addition, you can make sure that the psi lambda, the downwards maps, these maps here, they're contractive and approximately order zero, just as was possible for finite nuclear dimension. And if both A and all its tracial states are quasi-diagonal, if you don't remember or haven't heard what quasi-diagonal means, never mind, just take this as a side remark. Then in addition, one can arrange that the psi lambda are approximately multiplicative. And if you like, for nuclear C-star algebra, you can in fact take this as definition of quasi-diagonality. Quasi-diagonality means you have approximately you have finite dimensional approximate representations which are sufficiently faithful. And just as a warning, even for continuous functions on the interval, approximations like this with these convex combinations of contractive order zero maps, they're not completely straightforward to write down. It takes a little bit of working. It's a nice exercise. Okay, and a problem I'm interested in, but which I couldn't solve at all, unfortunately, is whether there's also a characterization of these CP approximations here, which avoids the maps psi lambda. And as I said, I couldn't do this, and I would very much like to see a proof, but it's bound to be hard, and you can see this from this statement here, because this would yield a direct proof that the completely positive approximation property passes the quotients. We know that nuclearity passes the quotients, but the proof goes via von Neumann algebras, goes via injectivity. There's no direct proof, at least not that I know, from completely positive approximation property to the fact that nuclearity passes the quotients. And yeah, I think this is a very intriguing problem. Okay, let's for the moment assume A to be separable, and in that case, of course, we can restrict to the case where the index sets of our approximating nets are just natural numbers. And then now I want to do the following. I want to think of this. So here we have A naught, and now I write it a little bit different. And here I have F naught. Sorry, this is not A naught. What am I doing? It's A, then I go to F naught, then I go back to A, I go to F1, go back to A, to F2, and so on. And then I can look at the compositions here, and then I get this system here. And this is now a system of finite dimensional C-star algebras and completely positive maps between them. In fact, completely contractive maps in most situations that we'll be interested in. And then I can look at a system like this by itself. And if A is nuclear, and if the system comes from an approximating system like this, then this system here will clearly encode all the information about A. Okay, that's the system I've written down here, and the rho k, k+1. They're just these compositions. They're these things here. Okay, and one should expect that this system here encodes all information about A, but it's a different question of how to extract this information. If you know you have a lot of money in the bank, but it's the weekend and you forgot your bank card, then it's not so easy to extract that money, even though you know it's there. And so some questions you can ask along these lines are, if you just write down the inductive limit of this, then you can, well, this is certainly a vector space, but you can of course equip it with more structure. And then you can ask what structure does the inductive limit have, or what in which category can you form an inductive limit? Okay, and you can also ask, can you see from such a system whether or not it comes from C-star algebra in the sense that that I described earlier, whether or not it comes from maps like this. I mean, I could just come up with a random choice of finite dimensional C-star algebras and maps between them, and could give it to you, and then can you detect whether this comes from a C-star algebra or whether it's something else? Okay, and even if you can detect whether it comes from a C-star algebra, can you then recover the C-star algebra from the system? And maybe in some cases you're not able to recover the C-star algebra, or maybe it's not the main task. Maybe you want to be able to read off pertinent information on A from this system, like K-theory, for example, or the trace space, or whatever.
Wilhelm, we had
yeah.
in the chat.
Oh, sorry. Yeah, I
that's all right. So this was Alan Dogon just asked, are the connecting maps approximately multiplicative in some sense?
Very good question. Can I postpone the question for a second?
Thank you.
So they're linear, they're completely positive, and they're not approximately multiplicative. If they're approximately multiplicative, then they would be, then you could replace them by multiplicative ones, and you'd have AF algebras, you'd have inductive limits of finite dimensional algebras. So that's too restrictive. But on the other hand, of course, they have to encode the multiplicative structure of A in some sense, and in which sense you'll see in a second. So here's the definition, which addresses this very question. It's a notion that was introduced by Blackadder and Kirchberg, and which Christian and I pushed a little bit further. So now let's consider again a system like this, where the FK are finite dimensional C-star algebras and the connecting maps are completely positive contractions. All right, and now I'm not assuming that there's a C-star algebra A waiting for me in the background. And then this system is said to be asymptotically multiplicative if the following holds. Now it's slightly complicated, but that's the information you have to keep track of. So let's go through this. Whenever you fix an index capital K and X and Y in Fk for that index, and you fix a tolerance, then there's another index M bigger than K, typically much bigger, such that whenever you have two further indices, little m and little n, bigger than this far bigger index, capital M, then if you look at the connecting maps from Fn to Fk, so those, and you compare them with those from Fk to Fn. I wrote it the other way around. From Fk to Fn, and you compare it with those from Fk to Fm, and then from Fm to Fn, then then rho mk may not be multiplicative, but rho mn is almost multiplicative, at least on the images coming from K. Okay, for X and Y in this finite dimensional set C-star algebra, and we're using that the unit ball is compact, of course. All right, and then so this is one way to capture the almost multiplicativity or capture multiplicativity of A in such a system. Then the system is asymptotically order 0 if the following weaker property holds. It's essentially, quantifiers are set up in almost the same way, but now I want that if these two elements X and Y, if they map to something which is almost orthogonal at the level M, then it maps, it keeps getting mapped to something almost orthogonal at the level N. Okay. And I don't want to go through the quantifiers again, but it's, I mean, here we capture multiplicativity and here we capture orthogonality preserving, this orthogonality preserving property. And this property will imply this, but this will not imply this. Okay, so far this was just a definition. And then here's the theorem using Blackstone and Kirchberg and these approximations by Brown, Carrion, and White. It goes as follows: let A be separable, unital, and nuclear. And unital, it's a bit of a red herring. It's much easier to state in the unital case. So let me do this. Then there exists a system of completely positive approximations such that the associated inductive system of the finite dimensional C-star algebras with these completely positive connecting maps has the following properties. It's asymptotically order 0 in the sense that I showed you. And moreover, when you look at this system here, then you can define an inductive limit inside this C-star algebra here. So this is bounded sequences in Fk, modulo null sequences equipped with supernal norm, and then you can think of the inductive limit of this thing, this system sitting inside here. It's not a C-star subalgebra in general, but you can think of this as a subspace. Okay. And you can take the norm closure where you take the norm of this C-star algebra. Okay, and then you have an induced map coming from the downwards map psi, from this psi k to Fk. You have an induced map from A to X. And since the psi k in the Brown, Carrion, White approximations could be chosen to be approximately order 0, then you can make sure that this induced map here is an orthogonality preserving map, and you can arrange things so that this is a complete order isomorphism. And let's say complete order isomorphism, then I think of X as an operator space, or in fact, you can think of X as an operator system sitting inside here. And now when I say operator system, then I mean a self-adjoint subspace of a C-star algebra, which carries an order unit, which is not necessarily the unit of this C-star algebra here. It carries an order unit, and that's just the image of the unit here. So the unit here goes to something, let's call it E. And this is a positive element. In X, it's also a positive element in the C star algebra here, and it's an order unit. It's an Archimedean order unit. Okay, and Blackadder and Kirchberg, they had already shown that if A is nuclear and if A is sufficiently quasi-diagonal, and let's even say that all the traces are quasi-diagonal, whatever that means. I know I haven't defined it and I don't want to. Then one can arrange, in addition, that the system is asymptotically multiplicative in the sense that I showed you earlier. But this doesn't cover all nuclear C star algebras, by far not. But you can also arrange in that case that psi is an injective star homomorphism. So in particular, this is a C star algebra. And you can even more arrange that that these connecting maps, they induce affine maps between the trace spaces. So these are the tracial functionals of norm at most one. Okay, and you have tracial functionals on fk plus 1. And the extreme functionals, they're just finitely many. They're 0, and the individual normalized traces on the matrix blocks, and then you have maps in the reverse directions, and they're affine maps, and these are affine maps between simplices, finite dimensional simplices, and then you can arrange things so that the trace functionals on A of norm equals 1 are just the inverse limit of these spaces here with these maps. Okay, so in this sense, if you have enough quasi-diagonality, if you can do this in an asymptotically multiplicative way, then you can read off the trace space of A from the approximating system in this sense. Okay, so there we have first bit of information of how to read off a very non-trivial property about A from the inductive system. Now, what's the upshot of this discussion? When you have a separable unital nuclear and say sufficiently quasi-diagonal C star algebra, by that I mean the traces are quasi-diagonal, the traces can be approximated by traces on finite dimensional C star algebras in a suitable way, then we know how to read off its trace space from the system of completely positive approximations, but we also know how to recover the multiplicative structure by looking at the map psi from A to this inductive limit in the category of operator systems. And this means, in particular, we can, of course, also describe projections and unitaries and partial isometries in terms of X. Okay, but once you can describe projections, unitaries, partial isometries, then you can describe K-theory. Okay, all you need to know for this to do this is to make sure that that all this is compatible with matrix amplifications, and this is certainly true. You can always amplify everything with the identity on matrix algebras or the compacts. Then everything goes through.
Is this known for MF algebras or NF algebras?
Sorry?
Was some of this stuff already known for the NF algebras or whatever?
Yeah, but it was never carried out. It was never really
Written down.
I mean,
Okay.
this appears in Blackadder and Kirchberg's paper, but they never really carried this out. And I think the reason why is that this only works for NF algebras, so only for quasi-diagonal nuclear C star algebras. But for K-theory, to work with K-theory, you really need you need to have extensions, and you need to have short exact sequences, and NF algebra's quasi-diagonality is not preserved under taking quotients. And I think that was the main drawback why this was never carried out, or why K-theory was never explicitly described for NF algebras along these lines.
Back even for things that aren't necessarily quasi-diagonal.
Say again.
You can recover the multiplicative structure even when, oh no, it does say sufficiently quasi-diagonal. Okay, so I'm a little confused, but okay, never mind. Okay, thanks.
Maybe you are referring to the next slide. So what do you do when you don't have quasi-diagonality? Okay, then we can still describe traces essentially in the same way as before. That works. But we can even describe K-theory. And in this context, along these lines, we can describe K-theory for nuclear C-star algebras in terms of these finite dimensional approximations. And this is because the downwards map psi, the map psi from A to X, is order 0. And how do we describe whether something is a projection in A? Well, it's a self-adjoint idempotent. And whether something is a projection in X, or it has the right to be called a projection in X, goes as follows. So P and A is a projection, even only if psi of P squared, it's not the same as psi of P, but it's the same as psi of P times psi of the unit of A. Okay, and what's behind this is a structure theorem for order 0 maps. A map, a completely positive map, is order 0 precisely if it can be written as a star homomorphism times a positive element which commutes with the image of the star homomorphism. And this is why we have this equivalence here. P is a projection even known if psi of P squared is the same as psi of P times psi of the unit equals psi of the unit times psi of P. Okay. and so this way we can describe projection, and you can use similar equalities to also describe unitaries and partial isometries. And again, everything passes to matrix algebras under amplifications. And so with this type of formula, you can always describe K-theory for nuclear C-star algebras by just looking at their approximating systems. Okay, and now this drawback that quasi-diagonality doesn't pass the quotients, this doesn't matter so much anymore, because now we can use this for arbitrary nuclear C-star algebras. Okay, and so now we can study nuclear C-star algebras in terms of their inductive systems, or finite dimensional C-star algebras if we only make these inductive systems asymptotically order 0, if they're of this form that I described. And but what I haven't addressed so far is whether if we're given an inductive system like this, can we characterize intrinsically when X can be equipped with the C-star algebra structure? And let's look at the unital case only. So this means we want that that X has an algebra, has an order unit E. So this is an Archimedean order unit, and this is in general, it's not the unit of this C-star algebra where X lives in it. It's really only an order unit for X, and it's in general also not invertible in any sense. I mean, not in the C-star algebra, which contains X. Yes.
Okay, sorry. I want to ask you a question about the previous slide. Can positivity can be defined in this setting? Because you already defined a projection. So in the previous slide, yeah, exactly. So in this slide, I mean that can positivity be defined in this setting? I mean that based on your map psi and I don't know psi of unital.
Positivity, yes, yeah. but psi, I mean positivity is the same on both sides. Positivity for X, I mean X lives in this big C-star algebra in this bounded sequence product of the FK modulo sum of the FK, and there you have, you know what positivity means, and X just inherits this notion of positivity. So that's the same. It's really only being an idempotent. It's the multiplicative structure that matters more. Positivity, it's related to the multiplicative structure, but it's not the same as being idempotent, of course.
I see. Okay, thank you.
So here we assume we have the unital situation, so X contains an Archimedean order unit, and then what we want for this intrinsic characterization of X coming from C-star algebra, we want that X squared being the same as E times X. Okay, and this is something that's going to happen when X comes from a system of the FK of A with these approximating maps, and once we have this, then we can use this to define a multiplication on X, say multiplication dot, and this goes like X dot Y times E equals XY, and this dot multiplication, this is the new multiplication. It's the multiplication of A we want to recover, and this multiplication here, this is the multiplication in the big C-star algebra which contains X. And then by defining this dot multiplication, this new multiplication on X, in this way, of course, you have to show that this really does define a multiplication, or you have to formulate the conditions for this system so that this really does define a multiplication on X. But then along these lines, you can characterize intrinsically only using the system itself, whether X can be equipped with the C-star algebra structure. You can recover the C-star algebra from X or from the inductive system. Okay, and I think time is running out. I'll skip the rest of the talk. There's just one more remark I would like to make. This way we can, as I said, we can characterize whether X or whether this system here defines a C-star algebra, and of course we should also be able to characterize whether the C-star algebra is nuclear or it should simply be nuclear, period. And it turns out this is possible by work of Sato and Ozawa separate. It's implicit in work of Ozawa and was spelled out in work of Sato. So we can, this will force the C star algebra X, the C star algebra A we recover from X along these lines to be nuclear. So we stay in this context. However, this will not spit out the actual approximations for A. Will not automatically spit out completely positive approximations, even if we plugged it in this system here. And this is again related to the problem I mentioned earlier, that that for these nuclear approximations in the sense of brown, curry on white, we don't have a one-sided version like we have for decomposition rank and for nuclear dimension. And this remains an open problem, and I'd quite like to solve this, because this then really would give a direct proof of nuclearity passes the quotients just using CPAP. But otherwise, that's more or less all I wanted to say, and maybe I stop here. Thank you very much.
Thank you very much. That was a great talk. We've already had a few questions, but perhaps there are some more in the audience. So I'll give people a chance to just go ahead and unmute yourself and ask. There's any questions?
Well, I have a quick question, I guess, if no one else does.
Sure.
Yep. So, I mean, I'm just wondering, so you say you have this characterization of when the system here comes from a C-star algebra, but is there any sort of natural way of actually defining the multiplication from just some arbitrary asymptotically or zero asymptotically multiplicative sequence of maps?
Yes. So, I mean, this. So this is how multiplication is defined in the in the inductive limit.
Mm-hmm.
Okay, and then you use that E is an order unit, and if you have you use that E times say C equals E times D for C and D in X, then C and D have to agree. So this is how you make sure that this really is well defined and that it exists. This comes from this property here. So at the level of the inductive limit X, this is very explicit, because from this property you get that this element X dot Y exists, and then you get uniqueness from this non-degeneracy condition here. and then this of course can also, all of this can be phrased at the level of the system itself. You can write this in terms of you just write X as you represent X by sequence and Y by sequence and E by sequence, and then you can make this explicit. Only it only looks very messy.
Right. Okay. Very nice. Thanks.
This can be done.
Great.
And one of the motivations, but we're very far from this, is to prove something like a Kunet formula for K theory along these lines. But this we haven't done yet.
But could it also potentially be a nice way of actually defining C-star algebras? Like you could somehow, instead of the sort of ugly definition you have of usually given of Jiangsu or something, you just find some nice sequence of these maps that maybe.
Yes.
Yeah. Nice.
Yes. Or I mean, yeah, or write a C-star attribute we already know and encode some hidden symmetries like for Jiangsu inside these approximating systems. But this hasn't been carried out yet. And of course, one thing you would like to do is combine this with additional features like Cartan subattributes and write these in such a way that Cartan subattributes or diagonals are being preserved. And then hopefully you'll be able to preserve groupoid structures.
Yeah, that would be very nice. Right.
Right. Do we have any further questions from the audience?
Yes, Wilhelm, first of all, thanks a lot for your great talk. So, and then, so in one of the theorems, you prove that for any separable nuclear C-star subalgebra, there is such associated interactive limit system with some nice properties.
Yes.
Am I right? Yeah. I think that, yes, in this term. So do you assume simplicity in that term?
No.
So, okay,
this
if you
completely general.
Okay, but okay, for example, if you take A to be a C of X, so there exists sort of associated inductive limits. So I'm wondering what kind of information can be encoded by these maps. I mean that by associated inductive system.
So for this statement here, we use these brown carry-on white approximations, and these are these convex combinations of order zero maps. Okay, and so for a when you take continuous functions on the interval,
yeah,
for example, then here you have the interval, and then what you would the standard approximations use these sawtooth functions, right? This is the most obvious ones. And you use partition of unity like this, and then from this you construct CP approximations. But these are not the ones that enter into this in this theorem because this I mean here you have two order zero maps, the green ones and the blue ones, but you don't have a convex combination. You add both of these order zero maps each with coefficient 1, and to have convex combinations and to make this theorem work, you have to solve this little exercise that I mentioned, and this goes as follows. You take something like this. And then you need another color, and now you make sure that these spikes stay away from the other spikes. And you take yet another color, and again make sure that these spikes stay away from each other. And then you add many colors like this, and then you take convex combinations of these. Okay, and all you have to do is make sure that these little spikes where two things do not overlap, where you miss the identity that these are pairwise orthogonal, so they in the convex combination they don't show up, they show up only in very small sense. So and you have to use approximations like this with these convex approximations, because we want to be able to we want our systems to be coherent. We want to be able to compose maps and still have norm control. So composition of maps also needs to be contractive, but also the individual parts, these order zero parts, they don't have to, they're not allowed to add up.
I see.
So yeah, from this, I mean, recovering the abelianness of continuous functions on the interval is easy. Recovering the covering dimension from this picture here is perhaps not so easy. So for covering dimension, you really want to remain in the nuclear dimension or decomposition ring setting.
And how about the cone semigroup? Do you think that we can say something interesting about the cone semigroup if there exists?
We haven't worked this out yet, but sure, this is also possible. I mean, you can just like you can describe Murray von Neumann equivalence of projections.
Yeah.
Using the multiplicative structure, you can also describe approximate Murray von Neumann equivalence of positive elements along these lines. Only it is very messy, and I would like to have a concrete approximation in mind before embarking on writing this down, because I mean, you have the approximations inside the Kuhn semigroup, and then you have to model everything inside the inductive system, and then the approximations that you have to use, they really keep piling up, and but in principle, this is possible. Yes.
Yeah. Okay. Thank you for your comprehensive answer.
Thanks for the question.
Do we have any other questions? If not, I have a very quick question. If this X, so at every point along the inductive limit, you have these finite dimensional algebras that are orthogonal in some sense with respect to your maps. Can you see X as somehow some sort of direct sum of orthogonal vector spaces in some sense, or completion of a direct sum of in some sense like this?
No, I don't think this is possible. No, I don't think so. I mean, certainly not in a direct sum. I mean, in the finite nuclear dimension setting, you might expect to be able to write X as a direct sum of D+1 spaces, but I don't think even that is possible, because you have to compose these decomposed maps with each other, and then your individual orthogonal parts, they keep being mixed. They keep being mixed again. So no, I don't see how this would be possible, but it's an intriguing question. Yeah, no, I don't know. I'll think about it a bit more.
Yeah, I'm thinking of something specific, but I'm maybe not able to phrase it quite how I want to. So, but yeah, so never mind. But do we have any other questions, or shall we thank Wilhelm again? Seems like questions are done, so thank you very much for this talk.
Thank you.
And if I could just take a minute to advertise next week's talk, which will be Sean Majid from Queen Mary. He will be talking about some non-commutative geometry of Poisson principal bundles. So we're back in quantum groups land next week. I hope some of you will be able to join us. And thank you very much for coming. Great.